like to look at today is how there are two different ways to solve problems with related rates if we have multiple variables going on. So let's look at this cone problem that is on your review. In this we have a cone, inverted cone, we have a radius of 50 feet, and we have a height of the cone of 100 feet. Now, the way we've been saying to do this sort of problem is when we have a water height here, it's what we're going to look at, we're going to figure stuff out. What I'm going to look at here, first with the volume equals 1/3 pi r squared times the height. What we always say first is there anything that doesn't change? Well, the volume is going to definitely change as the water level goes up and down, meaning the height will change, and as this water level goes up or down, the radius of the water will also change. So everything's changing, so that means that we have some fun things to do here. We're going to have to do a product rule. So, take the derivative of everything. dv dt will equal, I'll make this whole thing my first and h my second. So it's going to be first times derivative of the second plus the second times the derivative of the first. So bring 2 down in front, so now it'll be 2/3 pi times r dr dt. From here, we need to try to plug things in. Now, they want to know what the rate of change of the height is. So that means what I'm looking for is just this guy right here, dh dt. That means everything else I should be able to plug something in. So let's go ahead and do that. dv dt, how's the volume changing? Well, let's see what we got here. The tank measures 100 feet tall when the height is 32 feet. Okay, so the height's 32 feet, so I can plug that in for height. I also have here up 50 cubic feet per minute is what's being poured in. So that's why I have a positive 50 because that's how the volume is changing. All this 1/3 times pi, the radius squared. Well, what is the radius? It really doesn't say. Well, something we should notice here, though, is that the radius is equal to 1/2 of the height. So, if the height at this point is 32 feet, that means the radius should be half of that, which is 16 feet. So I'm going to have 16 squared. Again, dh dt is my unknown, so it's going to stay like that. And then what do I have over here? I have height is 32, multiply that by 2/3, by pi, by that radius again, and then the dr dt. Well, we really don't know what dr dt is. However, the little trick I can do, if I know this equation right here, that the radius and the height are related, that means that their derivatives are related. dr dt would then be 1/2 of dh dt. So I can just plug that guy in over here, 1/2 times dh dt. From here, I can solve it as such. We need to now do some simplifying here, so let's see what we got. We'll solve 50 over here on the left. 16 squared will give you 256 times pi divided by 3. We still have this dh dt going on. And then this guy, well, the 2's will cancel each other out, and what we'll end up with, we'll have 512 pi divided by 3, also with dh dt. So they both have a dh dt, and we both have something in terms of pi. So I can just combine these like terms here, and I'm going to end up getting 256 plus 512 gives me 768 pi up top, 3 on the bottom, and each has a dh dt term. Well, when I divide this, I actually get 256 pi exactly equals 50, and we still have dh dt on the end. So when I answer dh dt, to get it by itself, I'm going to divide by 256 pi. So 50 over 256 pi. That can reduce to 25 over 128 pi. My unit should then be feet per second. This is the method I prefer, just because I like going and doing the product rule, getting my couple different rates, and then comparing my new rates there as well. We have another option that we can do, though. So let's look at it in the other way. I'm going to start it the exact same way. Let's draw the same cone where I have a radius of 50. I have a big height of 100. And I have here still my water level is going to have a height of 32, which means we said the radius here then would be 16. Okay? We still say, same way we did before, the radius is equal to 1/2 of the height. It's all still important. Still need to look at that. We're going to start the same way. Volume equals 1/3 pi r squared times the height. Now, in this method, we want to immediately try to change and get it out of having these two variables where we have to use a product rule and try to make it into one variable. Well, first of all, what are we trying to find? The rate of change of the height. So that means I want to keep height the same, but I want to maybe change the radius into something that is in terms of height. Well, we talked about that already. It's already right here. The radius is 1/2 of the height. So all I'm going to do is change radius into 1/2 of height and keep everything the same and try to simplify before I even take this derivative. So I have volume now equals 1/3 pi times 1/2 of the height squared times the height. When I simplify this, 1/3 times pi, when I distribute this exponent, it'll now become 1/4 height squared, still times this extra height on the outside. Simplify it more, my fraction now is 1/12 pi, and I'll now have h cubed. This is a much easier item to take a derivative of. Volume and height are still both changing, so I just take my derivative like I normally would. dv dt will equal, when I bring the 3 in front, 3 over 12 becomes 1 over 4 times pi times the height squared, and because it's with respect to time, my dh dt term. And then all I do from here is plug in for what I, what I knew. My change in volume we said was 50, that's still the same. 1/4 pi times the height is 32, so 32 squared, and I'm solving for dh dt. So I should get here 50 equals, when I do this, the 32 squared divided by 4 gives me 256 pi, still dh dt, and this should look very familiar because we just did it on the last page, getting the exact same answer. dh dt equals 50 over 256 pi, or that reduced again to 25 over 128 pi, with my units again being feet per second. So either way you attack this, you still got the exact same answer, 25 over 128 pi, or back with this last way, we did it and we also had the same thing, 25 over 128 pi. Two different methods to do either of the ones when you have multiple variables. Now again, just for comparison, if this was, instead of a cone, if I said cylinder, something to think about with a cylinder is that as the water level changes, as the water level is going up and down, the radius is never changing. So I could go and plug in my radius immediately because that is always constant. Hopefully this helps, give you a little extra tidbit, and make sure you're ready to go for tomorrow, be able to do each and every kind on there.